Hello again, Algebra 2 students. Our video today is going to be on analyzing graphs of polynomial functions. So, a couple things to note. Turning points is a very important characteristic of a polynomial function. Turning points correspond to local maximum and local minimum values. A couple things for you to fill in your notes. The y-coordinate of a turning point is considered to be a local or relative maximum of the function if the point is higher than all nearby points. I'm going to draw a little sketch of a graph over here. Oops, not using white. So maybe I got a function that looks something like this when I graph it. I would say that I have a local or a relative maximum point right here at the top of a hill. This point is higher than all of the nearby points, so locally or relatively it is a maximum. Not the maximum of the whole function, because I know this function continues on forever to infinity, but in this general region this is the highest point, so that would be a local or relative maximum. On the other hand, y-coordinate of a turning point is a local or relative minimum of the function if the point is lower than all the nearby points, such as this one right down here. So we've got the bottom of a valley. In this relative region, this local area, this is the lowest point, so this would be a local or a relative minimum. And we're going to learn how to identify those using graphing technology. Now, both of these have a couple of turns. Now, this I would bet is probably some sort of cubic function. And I know that because I know something about the number of turning points of polynomial functions. So the graph of every polynomial function of degree n has at most n minus 1 turning points. Now, if you think about that, if I were to quickly sketch for you a couple of graphs, well, here would be x squared. Well, how many times does that turn? Just one time. X cubed might look something like this. Well, how many times does it turn? Once, twice. X to the fourth may look something like this. 1, 2, 3. Both ends head upwards. Remember, even degree functions have end behavior that matches on both sides, and it could turn 1, 2, 3 times on the way to doing that. X to the fifth, the same thing. Might go once, twice, 3, 4 turns on its way to heading down to the left and up to the right. So, at most, n minus 1 turning points where n is the degree of the function. Now, if a polynomial has n distinct real zeros, meaning it crosses the x-axis in exactly that many places. So fifth degree has 5 distinct real zeros, 5 separate places where it crosses the x-axis. Then it's going to have exactly n minus 1 turning points. That's not n. It should be n minus 1. Sorry about that. N minus 1. As in fifth degree's got 1, 2, 3, 4 turning points guaranteed because there were 5 distinct real zeros. Now, how to identify these different important aspects of a graph? Well, that's what we're going to do next. First, we're going to state the maximum number of turns that the graph of the function could have. Then we'll identify the real zeros of the function. Finally, we'll identify the points where the local or local relative maxima, maxima is the plural of maximum, and local minima, again, plural of minimum, occur. So this first one, x cubed minus 3x squared plus 2. First of all, the maximum number of turns, well, what we just learned is that the maximum number of turns would be 1 less than the degree. So since this is a cubic function, this one can turn at most 2 times. Now, to find the real zeros in the minima and the maxima, I'm going to resort to technology. For the first example, I'm going to show you how to do this on a graphing calculator. So if I were to graph that function, x cubed minus 3x squared plus 2, and I graph it in the normal viewing window, it's going to end up looking something like this. I can use my calculator to approximate the real zeros. It's going to cross the x-axis right here, and right here, and right here. To calculate those, I use the calc menu. Calc is right above trace on your calculator. So second and then trace takes to the calculate menu. We want to calculate the zeros of the function, so I'll choose 2. Now, to find these zeros, you have to tell your calculator where to look. I specifically want to find this 0 on the left. So I need to move the left bound. That's the question it's asking. I'm going to use the left and right arrows to move the boundaries. I use the left arrow to move the left bound to the left of the 0, which in this case would mean it needs to be below it. So my bound currently is at negative 1.06 and the y value negative 2.5. I just need to see a negative y value. I hit enter to set the left boundary. Now, to set the right boundary, my right boundary needs to be on the other side of the 0, on the other side of that x-intercept. So I hit the right arrow a couple times to move the boundary to the right, which in this case needs to be above the x-axis, which it is because my y value is positive. I hit enter. So now I'm telling my calculator, in between these two boundaries, what is the 0 of the function? As for a guess, I can hit the left arrow to move my guess back inside the boundary. You don't have to do that. But then you hit enter, and it will turn out a 0 for us. So in the worksheet that you're doing, it says round to the nearest tenth. So I would round this to negative 0.7. So I'm going to go ahead and write that down here. We've got negative 0.7. That's one of my real zeros. To find the other ones, I would repeat that process. Second, calc, the 0. My left bound now needs to be to the left of the next 0, so it needs to be just to the left of this. I'll stop it right there. My right bound needs to be on the right side, in this case below. Put it right there. Guess somewhere in the middle. Gives us the other 0. So that 0 is at positive 1. And I would, comma, 1. Comma, I could go back and find the third one, but for the sake of time, we're going to move on. So the next thing I'm going to find is any local minima or maxima. Well, I notice that there's one hill and one valley, which means there's one local maximum point and one local minimum point. And I can calculate those with my calculator as well. To do that, go back to the calculate menu. Second calc. This time, if I want to calculate the maximum, the top of the hill first, we would choose the fourth option, maximum. We'll scroll down in this case and hit enter. Same idea with the left bound and right bound and guess questions like it asked when we found the 0. So to find this local maximum point, I need to hit my left arrow key to slide the cursor over to the left of that maximum point. So it should go up and see it come back down. It's a little bit below the maximum. Hit enter. My right boundary, I need to move the right arrow. It's got to go up and come back down. I want to see it on the other side of that maximum point. I hit enter. Again, guess somewhere in between, and it will give me my maximum point. Now, it says something like this, 1.032 for e to the negative 6. Well, this, remember, is scientific notation. This means 0.0000001, which is really close to 0. Sometimes your calculator will do this when really it means 0. It just doesn't like to use 0. So the maximum here would be at the point 0, 2. I'm going to go ahead and write that down here for my maximum. It's at 0, 2. If I want to adjust the maximum value, that'd be 2 because that's the output. But usually we like to put the points where those maxima and minima occur. To find the minima, or minimum in this case, is just one of them. I'm going to repeat that process. Second calc, but this time choose minimum. So I'm going to calculate the minimum of this graph. Right arrow a couple times. Again, left bound, right bound, guess. So left bound on the left side looks good. Hit enter. And then right bound needs to be on the right side. Watch it go down and come back up. Hit enter. Ooh, a little too far, that's okay. Put your guess somewhere in the middle. Hit enter. And it picks out the minimum point. In this case, I'd round that to 2. 2.00. That many zeros means, again, my calculator just doesn't quite want to round it like I would. So 2, negative 2 would be the minimum point for that particular graph. Now, you could also do this same thing, finding zeros and finding minima and maxima using Desmos. And that's what I'm going to do for the next two that are a little bit bigger. So, instead of a graphing calculator, I open up Desmos and I graph the two functions that we're working with. So here they are. Here's the first one, x to the fourth, etc. Already graphed for us in green. Now as I do this, make it a little bit thicker, to find the zeros, I simply click on the x-intercepts here, 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 and I write down all those x values. That's pretty simple, folks. To find the local minima and maxima, now in this case, the number of turns, which we didn't answer here, if it's x to the fourth, there's a maximum number of turns that would be 3. Well, my graph actually has 3 turns in it. 1, 2, 3. Which means I've got multiple minima and maxima. So I've got one maximum because there's one hill. I have 2 local or relative minima because there are 2 valleys. Now to find these, and again, Desmos makes this super easy because all you have to do is click on those points. I could click on the bottom of this valley and the bottom of this valley. Those would be my 2 local or relative minima. I'd write down those points and be good to go. If I click on the top of the hill, there's my local maximum. One single point, that's okay. I write that down, there's my answer. Pretty simple, right? Now if I were to do the next example, again, I'll skip over that because we're just moving for time here. X to the fifth is going to have a maximum of 4 turns. Might have 5 real zeros, might have less than that. But again, the maxima and the minima, to find them, easiest way to do it is to graph it on Desmos, which I've got here. Here it is in blue. This one has only 3 turns. That's okay. Sometimes it doesn't. Remember, that's a maximum number of turns. Doesn't mean we have to have that many, but we could have that many. Looks like it has 3 real zeros because it crosses the x-axis in 3 places. 1 local maximum, 1 local minimum. Don't be fooled by this one. You could zoom in and notice it. Desmos also gives you the y-intercept, which is at 0, -1, and the maximum is minima is just to the left or right of it, excuse me. So there's my minimum, here's my maximum, here's my 3 zeros. I've got everything I need. I could write it down and be all done. So that's analyzing graphs of polynomial functions using a bunch of technology.